Okay, welcome everyone. Did you hit record?
Yep.
Woo!
I get it.
What's up? Good. Welcome everybody. Yeah, something's going on over there. All right, it is Tuesday, and last class, which was Friday, we had a test on Chapter 8. How'd it go?
Good. Great.
Woo! We also squeezed in, except it wasn't not really, into the very end of class. It was just on the board. A bunch of examples of a whole bunch of different vocabulary words regarding walks that one can take through a graph. Oh, I should also mention that the previous class we introduced graph theory. So here's what we have right now. We have a lot of graphs, man, and we have a lot of vocabulary. Just to throw out some of this vocabulary, we got, the graph, the subgraph, the simple graph, the multigraph, the adjacent, incident, degree, complement, handshake, bipartite, and we got a whole crap load of different examples. One reason to learn all these examples is because they help us explore various graph properties. All right, then the other thing that happened in section 10.2 was you learned about all these walks and trails and circuits and cycles. Let's go! Section 10.1 was, someone find me the good black marker and toss over here. Section 10.1 said, we're going to try to go over this very efficiently. Someone set a timer for 15 minutes.
I got you.
Good. Good.
Yes.
Woo. Okay, so wait, we don't have time to go over every single problem, so we're going to go over some of them or something. Number one, good. Number one said, produce the underlying simple graph for the following graph. That's just is this just problem not worth going over?
Yeah.
Yeah, what is the underlying simple graph? I'm not even sure I used this phrase.
We're still going over it.
We are still, it turns out that we are still going over it. This is the underlying simple graph. Essentially, all you are now doing is removing edges until, any two vertices which have an edge between them, any two distinct vertices which have an edge between them, remove all but one edge, and remove all loops. Is that correct?
Yes.
I feel that is correct. And so ultimately what we are doing is, determining for any two people whether or not they have some kind of relationship. Agreed? And we're ignoring the have relationship with yourself. All right, good. Next. I think, one piece of vocab I forgot to use 2 classes ago was this multigraph thing. When Gossett calls something a graph, he is saying that it may or may not have multiple edges between two vertices or loops. When he says simple graph, then it definitely does not have multiple edges or loops. When he says multigraph, he's specifically referencing that it does have those, or should. Okay, so cool? All right. Woo! Next, part 2 just tried to get you to spend some time and effort exploring various happy graphs that we should know about and writing down their properties. And the question is, is this graph bipartite? And the question was G and M. What did you get as your answer? Wait, G and M is just the graph. Wait, isn't that just the grid graph?
Yeah.
I thought the grid graph was always bipartite. Was that just wrong? Oh, okay. Yes. Okay, so for example, G23 or something would be the graph, which was like this or some crap, right? Chop, and then all my markers. Can I get a bunch of markers? Some reds and blues and greens, and don't throw them, just bring one. Good, thank you. Good, so we can see, given a particular graph, you can sort of show that it is bipartite with a coloring by sort of saying let this be red, and then this is blue, and then you can just go red, blue. Agreed? Who's following this conversation? Good. And note that if we think of the blue points as the frog gender 1 and red points as the frog gender 2, I know nothing about frogs, then every frog relationship is between someone from the red gender and the blue gender. Cool? Say cool. Woo! All right. And so all that these people are saying is there are some trivial cases to worry about, like what you have to have at least 2 points, I guess, for it to be bipartite. So that's all. Otherwise, the grid graph is always bipartite. Good. You know, I don't want to dwell too much on these like tiny special cases, but probably you do need to actually partition the graph into like non-empty subsets. So let's just agree that we're like either don't know or don't care what a graph with a single vertex is, whether it's bipartite or not. Can we agree that we don't know or don't care? Okay, good. Woo! More! Kn. What is Kn? That's the notation for the complete graph. Is that bipartite? I think just like full stop no, except for the trivial case in which n is 2. And can we maybe make a so let's just to draw a couple examples, right? That's like K3, that's K4, that's K5. Why did I draw it like that?
That's not K4. We need the things. Yes, the things.
Good. Good. Yeah, good. Okay, so these are just all just clearly not bipartite, right? Because like, so I guess the only time it's bipartite is if K is 2. Okay, good. More. Sn. What is Sn? That's like the star graph. Is that right?
Yeah.
He called Sn being like boom, and then there's like n total vertices. So he would call that S6. There's some controversy about this. But anyway, is this graph bipartite?
Yes.
Yeah, every star graph, in fact, is bipartite, right? Because there's one, say, you know, whatever gender frog, and then all the other frogs, man. That's what's going on. It's a harem of frogs. Yep. Woo! Next, the cycle graph Cn. Isn't that what Cn is? Isn't that the next question?
Yeah.
Good. So Cn, when is Cn bipartite? When n is even. Yeah. And so like, right? And then So now this is, for example, here C5. This is C4. Okay, this is just kind of playing around by example, but it seems like this is a This is a bipartition, which can happen when n is even. I mean, it will be bipartite, but when n is odd, it just can't happen, right? Because without loss of generality, if I assign a certain vertex to one of the sets of the bipartition, then its neighbors must be from the other set, and then we get an edge between two things in the same set. I need this one. So okay, good. So in fact, not only is it true that the cycle, not only is it true that an odd cycle graph is not bipartite, and then an even cycle graph is bipartite, but something stronger is possible. And this theorem is not stated so clearly in Gossage. It's kind of mumbled and jumbled, but like I think it's relatively standard in the world of graph theory to have this as a big important theorem. And so we're going to prove it in about 10 minutes, which is that a graph is bipartite if and only if there are no odd cycles. This is fairly suggestive that if there is an odd cycle, it is not bipartite. Agree? Okay. Who's paying attention to what I'm saying? If there's an odd cycle, it's not bipartite. But a much stronger claim is that if there are no odd cycles, it is bipartite. We're going to prove that in a minute. It's a little bit hard. Okay. That was a preview. All right, more. What else? That was 2. Can we just do a couple out loud? How about part E, the wheel graph? I don't really care about the wheel graph so much. It's like can't be bipartite, right? Like ever, unless W2 or something. Depends on how he defines W2. Let's just call that basically no, except for some maybe trivial annoying.
It has to be 4 or greater.
It's is that what he says?
He defines it.
Okay, cool. Okay, good. Next, getting slightly more interesting, arguably. 3B, draw each of the following complement graphs. This is just a way of getting you to play around with all the vocab. S5 is like the star graph. So if S5 is the star graph with 4 thingies, then the complement of S5 is the graph with, well, now you're just making like a graph of people if they're not friends, right?
Or one in the middle.
What's up?
No, good one.
I guess so.
So it's just like, so it's like
There's no
za,
Ns.
za, 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 za. Did I do that right? Yeah. Good. So in fact, it's just like the complete graph on all the vertices except the one in the middle. Is that right? I feel like that's right in general, right? The star graph is going to be the complete graph on all the vertices not in the center. Woo! Good, 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 good. That was the thing. 4B and 4C both ask you to draw the complement graph. Can we skip this?
Yes.
Good. 5A and 5B are more questions about vocab and stuff and regularity. They say, yo, is the complete graph of order n regular? Or for what values of m and n is the graph regular? Kn, for what values of k, this is 5A we're on now. For what values of 5A is it regular? Always, right? Yeah. A graph is regular if all the vertices have the same degree. Every complete graph is going to be regular because every vertex is connected to every other vertex. In fact, in a complete graph of size n or order n, every vertex has degree n minus 1. Cool. 5 minutes left. Good. 5B. Let's skip that one. 6 and 7 and et cetera, et cetera. How many edges does Kn have? Prove your result. How many edges?
Choose 2.
Yeah, this is just kind of like basic counting principles, right? If I have a complete graph, how many edges are there? Well, there's an edge between every 2 vertices. How many pairs of vertices are there? There are n choose 2 pairs of vertices. Like literally, that's what n choose 2 counts, right? It's the number of ways of picking 2 vertices from the set of n vertices. So if there are n choose 2 pairs, then there are n choose 2 edges in the complete graph. Cool, there's your proof. Woo! Combinatorial. How many edges does KNM have? Prove your result. Well, now we have KNM as the complete bipartite graph. So the bipartition here is like so, and this picture's getting a little complicated. But how many edges are there? Well, if there are n vertices in one of the sets and m vertices in the other set of the bipartition, then for each vertex in the first set, it's connected to m other vertices, and there are n of them. So I claim that there are n times n edges in the complete bipartite graph NM. Cool? All right, doing the graph theory. Woo-hoo! 8. Prove that no graph can have an odd number of vertices with odd degree. That was hard? Wait, that wasn't supposed to be hard.
That wasn't hard.
How can it? We'll prove that a graph cannot have an odd number of vertices with odd degree. Well, dude, you have an odd number of vertices with odd degree. Then when you add up all the degrees of all the vertices, you would get an odd number, because the sum of an odd number of odd numbers is odd. Want me to say that again? No, the sum of an odd number of odd things is odd. Did I do that right? Yeah. Because odd times odd is odd. Wait, hold on, let me write this down a little bit more clearly. This is number 8. Prove that no graph can have an odd number of vertices with odd degree. Okay, so it's something like, if you want to do this properly, what you can say is, I don't even know how to say this. Let S be the set of all vertices such that the degree of that vertex is odd. So this is the set of all vertices of odd degree. And suppose that the size of n is also odd. That's essentially what we want to show is impossible, right? This would be like the rigorous proof. Agree? Okay. Then, if you take the sum from I equals 1 to n of the degrees of all the vertices, then the sum of the degrees of all the vertices, can I just not write this all out? I could, but I don't want to. The sum of the degrees of all the vertices is the sum of all the odd vertices, the sum of all the degrees, the sum of all the even degree vertices, plus the sum of all the odd degree vertices. But of course when you add up any number of even numbers, it's even. And when you add up an odd number of odd numbers, it's odd. So the sum of the degrees of all the vertices would have to be odd. You want me to say that again more slowly, or are we cool? That is just impossible, because the handshake theorem says, as we proved last class, that the sum of the degrees of all the vertices is always even, because in fact it is just twice the number of edges. Right? That was the key. The key observation is that the degree of a vertex is the number of edges which are incident with that vertex. And since every edge connects two vertices, except for loops, but we count those twice to make it all work. Since every edge connects two vertices, every edge contributes to the degree of two different vertices. And therefore, I've just made a counting argument, I redid it last class, but we're redoing it now, that the sum of the degrees of all the vertices is twice the number of edges. So corollary, the sum of the degrees of all the vertices must be even. So we can't have an odd number of vertices. Cool, cool, cool. Woo, woo, woo! Graph doing the graph theory number 9 says, that's the time's up, but I reject that. Extremely predictable. Suppose G is a regular graph in which every vertex has odd degree. Okay, good. So regular graph, every vertex has odd degree, and so let's let that degree be like some number like 2n plus 1 or whatever. Okay, or 2n minus. It doesn't matter. Okay, so good. What the hell are we proving again?
Prove that the number of edges in G is multiple.
Prove that the number of edges in G is multiple. This is like not hard at all. Sorry, I changed my mind. Let this be 2k minus 1. Let 2k minus 1 be the degree of each vertex in this graph. And then if there are n vertices, that's a little more standard, is to let n be the number of vertices. Then what is the sum of the degrees of all the vertices? Let me make sure I don't mess this up. The sum of the degrees of all the vertices. Well, oh yeah, this is easy. It's just the number of vertices. Wait, hold on. Am I doing this right?
Yeah.
My notation is a little bit weird.
Wait, with
No, I feel like it's okay.
Every vertex has an odd degree.
Every.
Well, they say every vertex has an odd degree k.
Oh, yeah.
Oh, they already introduced k? I apologize.
Oh, I thought you meant like k is.
So k is odd. It's just like built into the problem.
I used to be online.
There are two, we investigated this last week. Was anyone here for this? There are two slightly different versions of Gossett that like have the same ISBN. They're like not a separate edition and they're not marked. It's just like occasionally in this chapter, like he found some mistakes and he like quick changed it or something. Okay, but anyway,
We should all switch to their graphics.
okay, hold on. Staying focused, staying focused. Anyway, what is this trying to say? We have a regular graph, so every vertex has the same degree. Also, every vertex has odd degree, and let that odd degree be k, just so we're all using the same letter. So k is not a number. Cool?
Yeah.
Well then, this is just kind of dumb, because the sum of the degrees of all the vertices is just nk. Is that what we were trying to do?
That's what we're trying to do.
No, not quite. We're trying to show that the number of edges is a multiple of k. But the number of edges just will be a multiple of k because this is also, wait, hold on.
Because it's 2 times.
This is twice the number of edges. Oh wait, why am I allowed to just divide by 2?
Because K is odd,
So that you can do that, it adds up to a
Just
grade,
did the other thing, right? Like,
something like that.
no graph.
Oh.
We have to have it in uneven numbers.
You have to have an even number.
Brilliant.
Yeah.
That's brilliant. Okay, so by number 8, which established that you cannot have an odd number of vertices of odd degree, what do we know? As this graph has all vertices of odd degree, n must be even. N must be even. In other words, there must be an even number of vertices in this problem, because there can't be an odd number of vertices, because if they all had odd degree, that would violate the Hamilton problem.
Yeah.
So since n times k is 2 epsilon, then epsilon is n over 2, which we know to be an integer times k. So k indeed does divide the number of edges. How are we doing? Some good math going on here. Notice how everything's coming up? It's just like counting and combinatorial reasoning and number theory. All right. This goes on forever, this song assignments. Show that if G is a simple graph with n vertices and epsilon edges, that epsilon is less than or equal to n choose 2. That's just dumb, right? The most number of edges possible is the complete graph n choose 2 skip. Woo! Next! 9, 10, 9, 10, 9, 30, 11, 12. How many edges are there in the complement of G? This is also easy, right? It's just n choose 2 minus epsilon. Done. That was 12. 14. If G has 10 edges, do we need to do this?
No.
G has 10 edges, and the complement of G has 5 edges. How many vertices does G have?
And choose 2.
So n choose 2 equals 15, then you like solve?
Yeah.
Done. Good. 14. 15. G has J edges, and the complement has K edges, where 2 times J plus K equals n. What? What'd you get for 15?
N plus 1.
Was it like easy?
Yeah.
Okay, good.
It's M plus, yeah.
Do you want to talk it out?
No. Maybe we should.
Maybe we should.
If you write for N
Oh,
choose
I just
2.
We should probably just write it out. Just what did he just because they're not probably bad.
Yeah, what are you doing?
I mean, I get it.
Good. Put your phone away. Good. Number 15. Good. G has J edges and G complement has K edges, where 2 times J plus K is M plus 1, and J is edges in G, and K is edges in G complement. And then the task is to do what? How many vertices does G have?
No, I didn't.
No,
Oh.
you copied it down wrong.
Are you sure?
No, you're right.
So don't we just know by the previous problem that the number of edges in G plus the number of edges in G complement has to be like n choose 2. Agree? Where n is the number of edges. So then does this just turn into J plus K equals n minus 1 over 2?
Yeah.
That's just it, man. This is just the whole problem. So J plus K times 2 is n minus 1. And so this works if like n is m plus 1. Wait.
Yeah.
So the answer is m plus 1 versus. Alright, that was 15. Oh good, we're getting the home stretch. 17. Let G be a simple graph with at least 2 vertices. Prove that there must exist 2 vertices that have the same degree. Ooh, a classic problem that some year I even put this on the test from the previous chapter, the 2 chapters ago. Simple graph with at least 2 vertices. So simple graph
That's what I thought was what I would.
with greater than or equal to 2 vertices. And what we need to prove is There must exist two vertices with the same degree, yeah. There must exist two vertices with the same degree. Alright, one way to think about this is if you have a whole bunch of people, you count all of their friendships, put an edge between them if they're friends. There must be two people with the same number of friends. Agree? There must be two people with the same number of friends. Okay, this is a classic graph theory result that is really just a direct application of the pigeonhole principle, although you have to be a little bit subtle about it. Because, so let there be, suppose there are n vertices. Suppose there are n vertices, and n is greater than or equal to 2. Well, is it possible for all the vertices to have, let's just talk it out first. Is it possible for everyone to have a different number of friends? First, seemingly maybe. Because what are the possible degrees? Yeah, what are, name, if you have a graph with n vertices, what are the possible degrees that any one vertex could have?
0 through n minus 1.
0 through n minus 1. Right? Because you could be friends with no one, or you could be friends with everyone. So if each if each vertex has n possible degrees, and there are n possible vertices, then it doesn't immediately show why the pigeonhole principle is possible. So that's why this is not that simple a problem. There's a little bit more going on.
If someone's friends with everyone who's without a friend, they will eliminate a box of people.
Yeah, if you don't really have full freedom, right? Because you can't have someone who's friends with no one and someone who's friends with everyone. Right? What if there was some like go-getter kid in high school who was like, I'm gonna make friends with every single person in this high school. That's my goal. And they wrote that on their like, like Eagle Scout like application or something. Like that's my plan. I'm gonna make friends with every single person in the whole school. But then there was just some misanthrope who was just like, my plan is to have no friends in high school. Then like those both can't be true, right? You can't have someone that's friends with no one and someone that's friends with everyone in the same school. So you can, in other words, you cannot have a vertex with degree 0 and also a vertex with degree n minus 1. Everyone go, oh. So really, this is like, there needs to be like a case argument going on here, right? There are really like two cases, I suppose. Is there a vertex with degree 0? Suppose the answer is yes, right? Answer 1, so case yes. There is a vertex. With degree 0. But now, if there's a vertex of degree 0, then no vertex can have degree n minus 1. So, how many possible degrees are there? Psst. How many possible degrees? N minus 1. So, there are n minus 1 possible degrees. Those degrees being 0, 1, 2, all the way up to n minus 2. Who's with me?
Yeah.
This is not maybe the most elegant way of writing this, but maybe it's not so bad. What about the case where the answer is no, that there is a vertex with degree 0? Well, now how many possible degrees are there? Then there are n minus 1 possible degrees. Again, what are those degrees? 1, 2, 3, n minus 1. I think the no case would have been easier to do first, but anyways, there it is. Okay, so in either one of those two cases, does everyone now agree that there are really only n minus 1 possible degrees, right? So now there are n minus 1 possible degrees, but n vertices. So by the pigeonhole principle, right, n minus 1 possible pigeonholes, n pigeons. By the pigeonhole principle, 2 vertices have the same degree. 2 vertices have the same degree. All right, how we doing? Good? Okay, good. We push on. 18, A and B. Oh, this is the theorem that we're going to prove, so let's skip this. I didn't mean to assign this problem. Or should we just do it right now in position? Yeah? Okay, good. Get a whole fresh piece of paper for this, though, because this is like a serious theorem of graph theory. This is like, you know,
B is the odd cycle one.
this is like you just walk into your Google interview or whatever, can you erase that board? And they start talking about bipartite graphs, and you're just like, well, as everyone knows, a bipartite graph exists. A graph is bipartite if and only if there are no odd cycles, etc., etc., etc. Okay, good. Erase faster, but also very thoroughly. Turn the camera, we're going to do it over here. No pressure. Good.
More pressure, you have to get it all the way off.
More pressure. Oh boy. That's hilarious. Good. So, theorem. That was just good. Theorem. G is bipartite if and only if G has no odd cycles. Theorem. G is bipartite if and only if G has no
Okay, that was
odd cycles. Ready? Hold on, Alvin, let's do it. First, let's go in the forward direction. Is this what I want to do first? Sure. Yeah. Okay, good. Good. I will show that it is impossible for a bipartite graph to have odd cycles. Should we draw like a little picture first and just like talk it out?
Sure.
Okay, here's the like talky way to do this. That's like doesn't really work. But it's worth getting some sort of feel for this. So suppose this is good. Suppose this is the bipartition. So you have 2 vertices in set A and 3 vertices in set B. Is everyone okay with me referring to this as bipartition? You just like can't get any odd cycles, man, because these are the male frogs or whatever, and these are the female frogs, and the male frogs are only friends with the female frogs, and that's all there is. And so, like, you can't have an odd cycle because what would it mean to have an odd? What is an odd cycle?
I just feel like I'm outnumbered.
You gotta get back where you started, right? But then, like 1, 2, just say some words.
3.